I wanted to find out what happens to charged particles in conductors. We're told that they go to the surface of the conductor. So if you add extra charge to a conductor, they'll run to the surface. And so the other thing that I wanted to do was to apply an external field, because even inside an external field, as long as it's a static field, we still expect there to be charges only on the outside. In the Griffith's E&M book, it talks about how there's a little footnote when it talks about that, says that that's actually only true in 3 dimensions, that in 2 dimensions that doesn't happen. And so what I wanted to do was to build some software to enable me to compare 2 and 3 dimensions. So, I'm constantly calculating the potential between 2-point charges, and it's really just, 1 over the distance between them. Okay, so all of this is unitless, no 4 pi epsilon naught, any of that crap. But I also have to keep them inside a boundary, and so what I've decided to make is either a circle or a sphere. So if the particular particle is outside of some magnitude of the radius, then it's going to encounter a ramp, a very steep ramp, that'll push it back inside. And once it's inside the circle or sphere, it'll experience no potential energy, so there's no forces due to that. I use the subsets command so that you can carefully figure out all of the pairs that you can have. Every particle has to interact with every other particle. So the subsets command in Mathematica is really nice for that. For the field, I just really take the second component, and so essentially call that the y component. So it's some field strength times the y component, and everybody, we total it up, so everybody contributes that much more energy to the system. So we've got the wall, we've got this is the wall, this is all of the pairings, and this is the external field. Then I just do it with a Lagrangian approach with a little bit of friction involved. Okay, so if we do it in 2 dimensions, come down here, all the rest of this is just getting my initial conditions set. One really nice thing about Mathematica is that it allows you to name your variables in a very fancy way, so I'm able to keep track of both the XYZ component and which particle it is this way. So my initial positions are just random, and my initial velocities are all 0, so I'm just setting them still. So if I evaluate this, it takes a little while. This is the 2-dimensional version, and so we can see we have 10 particles, and there's a first component and a second component for everybody. So if I take a look at what this looks like, we see a nice circle, and we see the particles. And so if I actually let the movie play, they sort of run around from each other for a while, and they go down. And it's because I didn't bother with the extra negative sign in defining my potential. And so most of them go onto the outside, but notice that there's one particle that sits and floats around on the inside. So let me just pause it at the very end. And you can see that this is sort of the lowest energy state the system can get to. Most of them are on the surface, but there's one that's floating around in the middle. Let's see what happens if we do it in 3 dimensions. Okay, I ran it in 3 dimensions. I had to pause it because it took a little while. You can see that now that sure enough there's an x, a y, and a z component for all 10 particles, which means that the differential equations we had to solve, there were essentially 30 independent variables that needed to be solved for, and I only go out about 5 seconds. So let's watch what this looks like. And now you see the sphere. That is, you have to stay inside the sphere, and you see all of the particles. Let's watch the movie. They float all around. This dimension here along this edge is the y-axis, and so we expected them all to come back in this direction. Now it's hard to see. Let me just pause it at the very end, and let me tilt it around and see if they're all on the surface. Sure enough, all 10 particles are on the surface. They've been pulled in this direction due to the electric field, but they're on the surface. There's none that are floating around on the inside like there was in the 2-dimensional case.